Good morning, all of you. Last class, we have seen different types of lenses: convex lens and concave lens. And how can you define a lens? A transparent material bound by two surfaces, of which one or both surfaces are spherical, forms a lens. There are two surfaces, and both surfaces can be spherical surface, or at least one surface should be spherical and other can be plane. This means that a lens is bound by at least one spherical surface. So all should remember definition of a lens. I repeat, it is a transparent material bound by two surfaces, of which one or both surfaces are spherical, forms a lens. This means that a lens is bound by at least one spherical surface. Okay? So one spherical surface and other will be plane. So two different types of lenses. One is convex lens, another is concave lens. So how can you recognize convex lens? This is the convex lens. There are two. Here I am marking the first diagram. Two surfaces. Surface number one and surface number two. Both are spherical. Okay. So here two spherical surfaces are there bulging outwards. Or one surface can be spherical bulging outwards and other can be plane. One is a spherical surface, other is a plane surface. Concave lens, you have two spherical surfaces. Okay, two spherical surfaces here, and they are curved inwards. First surface and second surface. Or at least one surface should be curved one, the spherical surface, the other surface can be plane surface. So this is the first surface and second surface. So you can see the definition again. It's a lens means it's a transparent material bound by two surfaces, two surfaces should be there. Okay. Of which one or both surfaces are spherical. In this diagram, both surfaces are spherical. Here one surface is spherical, other is plane. One surface is spherical, other is plane. So how you recognize the convex lens and concave lens? You can see there this spherical surface here. The two surfaces are there bulging outwards. Okay. A lens may have two spherical surfaces bulging outwards. Such lens we call it as convex lens. Okay. Bulging outwards, convex lens. And here you can have two, this is again spherical surface, but it is curved inwards. And two, this particular lens we call it as two surfaces are there, so it is called double convex lens. So we call this as double convex lens. Double convex lens. Double convex lens mean both surfaces are spherical. Here both surfaces are curved inwards, so it's a concave lens. So it is called double concave lens. Double concave lens. And here this is one surface is plane and other is curved surface. So we call this as plano-convex lens. Plano-convex lens. Here one surface is plane, other is concave shape. So we call this as plano-concave lens. Okay, plano-concave lens. So this is the way we classify. Now other speciality here, you see here, in the case of a convex lens, okay, you can see that it is thicker at the middle region than at the edges, okay, here. And in the case of concave lens, you can see that it is thicker at the edges than at the middle. So this is the way how you can touch and recognize them. So here you will see that means convex lens, it is thicker at the middle than at the edges. This is the way you recognize. And here it is. In the case of concave lens, it is thicker at the edges than at the middle. So this is another way you can say, recognize. You can recognize it. So I repeat, convex lens is thicker at the middle as compared to the edges. Okay, and concave lens, it is thicker at the edges than at the middle. And convex lens is also known as converging lens. Why it is there? On the way. It's also convex lens is known as converging lens and concave lens is known as diverging lens. Why we'll be explaining on the way. So these are the main points. Convex lens is known as converging lens and concave lens is known as diverging lens. So in the next diagram you will recognize that. Okay, now you will recognize what is the center of curvature, optical center, etc. So that will be the next point. So we usually consider thin lenses, convex lens or concave lens, thin convex lens or concave lens. And here you have your convex lens. We usually take double convex and concave. So there is no need of mentioning always double concave and double convex. It's a simply convex lens we'll take like this. Okay. This is the first surface and this second surface, and this is the first surface and second surface. So we have to mark the centers of the two spherical part. First surface, you can see that it is a part of a sphere like this. We extend like this. Therefore, there will be a center for this first curved surface. Its center will be here. So I am marking it as C1. C1 is the center of curvature of the first surface. It is lying on right side for convex lens. It is called center of curvature of the first spherical surface. Similarly, in the case of second surface you take, second surface is curved like this. It's a part of sphere like this. So its center will be is here on left side. So that we mark it as C2. So C2 is the center of curvature of the second spherical surface of convex lens. See? Okay? So C1 is the center of curvature for the first curved surface and C2 the center of curvature for the second curved surface. Okay, similarly, if we mark for concave lens, suppose we are marking for concave lens, just see. Concave lens. So concave lens, you have the first surface here. This is the first surface. This is the first surface. If we are extending that, it will be like this. So where will be the center of curvature of the first surface? It is on left side. So that I am marking it as C1. And for the second surface, if you mark like this, a curve like this. So center of curvature of the second surface is lying on right side C2. See the locations. These locations are important for you. Okay, C stands for here center of curvatures. C1 for the first surface and C2 for the second surface. And we are drawing a straight line passing through C1 and C2, and that straight line we call it as principal axis. So define principal axis of a lens. It is a straight line passing through the centers of curvatures of a lens is known as principal axis. So this we call it as a principal axis. Principal axis of a lens. I think this point is clear to all of you. It's imaginary straight line passing through the two centers of curvature of a lens is called principal axis. Very important point. So you can recognize from this diagram. So principal axis. Next point, one more point we'll add. You can see a center point on the principal axis which is inside the lens, center point of lens, which is lying on the principal axis. We call it represented by O. Okay, here this is the center point of the lens and which is on the principal axis, and this is represented by letter O, and this is known as optical center. Optical center. Optical center. So the point O, we call it as optical center. You have to remember what is optical center. So the center point of lens is its optical center and is usually represented by the letter O. So what is the speciality of optical center that I'll explain? If a ray of light passes through the optical center and it goes without any deviation. Without any deviation, that definition I'll give when I complete the next diagram. That is for principal focus. So this is the cases. One is a principal axis. Principal axis mean it is an imaginary straight line passing through the centers of curvatures of the lens C1 and C2. So location of C1 and C2, please remember. Okay, principal axis and center point of the lens, which is on the principal axis, called optical center, represented by O. And next, one more term is there. What is the meaning of aperture? Okay, what is the meaning of aperture? Aperture means it is the effective diameter of the circular outline of spherical lens. What is the meaning of that? Effective diameter of the circular outline means from here, I am showing here, this much peripheral portion, we call it as aperture. Okay, this is what we call it as effective diameter of the circular outline of a spherical lens is called its aperture. You can measure along a tape, you can keep and measure this. This is called its aperture. So in this chapter, we discuss only with what? Thin lenses, very thin lenses. Thin lenses mean the aperture is very small and it is thin. And C1 and C2 are equidistant from optical center. So these are the very important point. Next, another point is, what is the principal focus of a lens? So we marked C1, C2 and O. One more point, we marked that, define principal focus. That is the next point. That is a very important one. Principal focus. Principal focus of a lens. Principal focus of a lens, represented by capital F. We have seen similar case in the case of mirror also. Okay. So, principal focus. So, this is your convex lens and concave lens. The straight line passing through the centers of curvature, we call it as right side. I'm marking for optical centers. So, C1 and C2. So, here we have, this is a straight line passing through the centers of curvature, that we call it as a principal axis. Yes. If the object is at infinity, the rays are parallel to the principal axis. Object we consider at infinity, infinite distance. Light rays coming from the sun. Object at infinity, rays are parallel to the principal axis, also parallel to themselves. Yes. These are the rays. So you can put one or two dotted lines so that the rays are coming from, to recognize that they are coming from infinite distance. They are parallel to principal axis, parallel to themselves. So refraction is going to take place here. We are showing only one bending. Actually, in lenses there are two refraction. One will be at this point from rarer to denser, and second from denser to rarer. That I'll show separately later. Okay. So these rays after refraction, rays parallel to principal axis, after refraction, they are converging, coming to a point. Yes, this is the way. You can see that they are coming to this point. Yes. So all are meeting at this point. They are converging to this point. So this point on the principal axis, we call it as principal focus. Okay. Principal focus. Similarly, in the case of concave lens, rays are parallel to principal axis, parallel to themselves. Object is at infinite distance. Example, light rays coming from the sun. Rays are parallel to themselves, parallel to principal axis. After refraction, they diverge and it goes like this. And if we extend backward, appears to come from a point here. So this also go after refraction goes like this. And this ray appear to come from this point. Similarly from here also. So this ray will after refraction goes like this. In this way. Appear to come from here. This ray after refraction diverge and goes like this. And extend back, appear to come from here. So this point we call it as principal focus. We mark it as with the capital F. Yes. So how can you define principal focus of a lens? So this is the definition that is in front of you. Rays parallel to principal axis after refraction changes the path, bends. Okay, changes the path after refraction, converges to a point on the principal axis in the case of a convex lens. Whereas in the case of concave lens, appear to diverge from a point. Appear to diverge from a point in the case of concave lens. This point on the principal axis is known as principal focus. Okay, this is the definition of principal focus along the diagram. It's a board question. So, how can you define principal focus of a lens? Rays parallel to, I repeat, rays parallel to principal axis. This is a diagram, figure 1. After refraction, converges to a point in the case of convex lens. This point on the principal axis is known as principal focus. Similarly, in the case of concave lens, rays parallel to principal axis after refraction appear to diverge from a point on the principal axis. This point is known as principal focus. Principal focus. Okay. So, usually, as a note for you, there are two refractions in a lens. One is from rarer to denser, another is from denser to rarer. But we'll show only one kind of bending, and this kind of two refraction exact diagram we'll recognize in class 12th. Okay, just for example, here you can see suppose this is a convex lens, this is a principal axis, one ray is coming parallel here. So at this point A, it is entering from rarer to denser medium, bends toward the normal. So it comes like this. At the point B, again it goes from dense to rarer, again bends away from the normal. So and finally comes here. So two refractions are there. Instead of showing this, we'll show for a thin lens, we mark only like this. Ray parallel and keep at the middle and bends toward the normal. So this is the way we'll show. So you have to just recognize that actually there are two refractions in a lens. It's rarer to denser at this point A and from denser to rarer point B. Effect is exactly same way we are recognizing. So exact diagrams we will see in the higher classes. Next, another point I want to share with you. So we want to see the image formation in the case of lens. For that, so we have to mark focus on right side and left side. So here you see the focus I marked on right side for convex lens, and the focus here I marked here for concave lens, it is on left side. Considering as per sign convention, object is on left side. Object is on left side. Suppose the object is on right side, you place. The object is on right side. Then In the case of convex lens, light rays converges to a point on the left side. That is also another focus. So you have a focus on right side as well as on left side. There are two focuses. So object on left side, then the focus is on right side. You can keep the object on right side, then the focus will be here. So all the rays will be converging to a point on left side. So that is also focus. So for a lens, there are two focuses, principal foci, we call it as. One is on right side, another is on left side. Here it is, when the object is on left side, it is on left side. When object is on right side, it will be on right side. So right side 1 and left side 1. Left side 1 we mark it as F1. Right side 1 we mark it as F2 for just to recognize the positions of the image. So what I'm going to do in the next diagram to familiarize. Suppose you take a convex lens. Okay, we are not seeing the surfaces, which is first one, second one. So right side of the focus, what we mark it as F2. Okay, and left side what we mark it as F1 and 2F1. And here it is F2 and 2F2. This is for sign convention, easy to recognize. So right side, the focus, we call it as, recognize as F2, on left side it is F1. In the case of concave mirror also, same way you can recognize. Okay, optical center, left side one, we mark it as F1. So we can mark it as 2F1. Right side what we will get it as F2 and 2F2 you can mark it as. So there are two principal focus. So you have centers of curvature on right side as well as left side. So there we are not marking there. We usually write the object position. Okay, the object will be beyond 2F1 or at 2F1, between F1 and 2F, etc. So we take. So these are the different locations. So define principal focus and the distance between. You can see that object on left, distance between optical center and the focus is called focal length. What is the focal length of a lens? Represented by small f. Distance between optical center and focus is called focal length, represented by f of a lens. So when object is on left side, object here on left side, so you see the focus here. So optical center to focus distance is called focal length. Object on left side, optical center to focus distance, we call it as focal length of a lens. You can compare with mirror. Now image formation in the case of convex lens is similar to that of concave mirror, and image formation in the case of concave lens is similar to that of convex mirror. The convex lens equivalent to concave mirror in image formation, and concave lens is equivalent to convex mirror in image formation. So same way we'll recognize. So before going to see the image formation by these lenses, we are to consider different rays. So we should require two rays for the image formation. So what are the different rays to be considered for image formation? Okay. For that, next point we are going to discuss. Image formation in lenses using ray diagrams. For that, what are the different rays to be considered? What are the different rays to be considered? There are so many light rays coming from the object. So what are the rays to be considered? First one, convex lens, concave lens, principal axis, ray parallel to principal axis after refraction passes through the focus. This is the first point. Ray parallel to principal axis after refraction passes through the focus. F2, that is on right side. Okay. In the case of convex lens, if it is in the case of a concave lens, you can take this one, ray parallel to principal axis. After refraction, it appears to come from a point that is F1 from the principal focus. First line, first ray parallel to principal axis after refraction passes through the point, passes the principal focus that is on right side of convex lens. And in the case of concave lens, ray parallel to principal axis after refraction appear to come from the principal focus F1 that is on left side. So this is the first point we have to consider. And second point is, if a ray of light is passing through the focus, then what will happen to it? This is the second diagram. So there are three cases we consider in the case of lenses. Left side we have F1 and right side we have F2. Yes. If a ray of light is passing through the focus F1 after refraction, then it becomes parallel to the principal axis. In the case of convex lens, you can see that a ray of light is passing through. If a ray of light passes through the principal focus F1 here, after refraction, you can see that it goes parallel to the principal axis, Okay, in the case of concave lens, how will you draw the diagram here? So we mark the principal F1 is here on left side, F2 is here on right side. You draw a light ray that tries to pass through F. If you extend that would touch F2. So if light ray reaches the concave lens and tends to pass through F2, okay, it cannot go there. After refraction, it becomes parallel to the principal axis. Parallel to the principal axis. So I repeat for the second one, ray passing through the principal focus of a convex lens. After refraction, becomes parallel to the principal axis. A ray tries to pass through principal focus of a concave lens after refraction becomes parallel as shown in figure 2. And one more case, that is the definition of optical center itself. We consider thin lenses. So how can you define optical center? Of course, it is the center point of the lens which is lying on the principal axis. But one more point, you define like this. So optical center means if a light ray is passing through this optical center, it goes without any deviation. Goes straight. So this is the term. So optical center is a point, center point of the lens which is lying on principal axis. If a ray light passes through that, goes without any deviation or bending. So no deviation, no bending for this. So this is the complete definition of optical center. So these are the different points. So three cases for image formation. What are the three different cases that we are to discuss? So I think all of you can recognize these diagrams. Three diagrams. So today's important points. Define principal focus of a lens. So whether it is a concave lens or convex lens, you can refer to the previous diagrams and just see rays parallel to principal axis. After refraction, converges to a point on the principal axis in the case of convex lens. So that point is called principal focus. And the distance between optical center and the principal focus is known as focal length of a lens, represented by small f. And in the case of concave lens, rays parallel to the principal axis, after refraction, they appear to come from a point on the principal axis. This point is known as principal focus. The distance between optical center and principal focus is known as focal length of the lens, represented by a small letter f. What is the unit of focal length? Unit of focal length, it is a length. So the unit is centimeter or meter. If it is SI unit, it should be in meter. So it can be represented in units, centimeter or meter. SI unit of focal length is meter. Take care of this point. Okay. So we have usually if the object is on left side, then the principal focus is on right side. If we keep the object on right side, then in the case of convex lens, you will get the focus on left side. And in the case of concave lens, it will be again on right side. So we have two principal foci for a lens, f1 and f2. Usually for convenience, f1 you mark on left side for concave and convex, and f2 we mark it on right side. f1 to f1, f2 to f2. Whether it is a concave lens or convex, it is convenient for recognizing the positions of the object and the image formed. Now regarding the image formation, we require minimum 2 rays to show the image formation in the case of convex lens or concave lens. For that, we require certain rays. What are the different rays to be considered for the image formation in the case of lenses? So there are 3 cases. Okay, in the case of mirror, we learned 4 cases. Here it is 3 cases. What is the first case? Refer to the above diagrams. First one is ray parallel to principal axis after refraction passes through the focus. In the case of convex lens. And for concave lens, ray parallel to the principal axis after refraction appear to come from a point. That point is called the focus. Appear to come from the focus. That is the first case. Second one, if a ray of light is passing through principal focus, then after refraction from the convex lens, it becomes parallel to the principal axis. Ray is passing through principal focus and reaches on convex lens. After refraction, it becomes parallel. Same point, if you go for a concave lens, you can see that ray of light reaching on concave lens and tends to pass through focus. Ray of light incident in such a way that tends to pass through the focus, then after refraction, it becomes parallel to the principal axis. That is the corresponding point in the case of concave lens. Now, most important point is third one, if a ray of light is passing through optical center, goes without any deviation, whether it is for a concave lens or convex lens. This is especially for thin lenses. We consider only thin lenses. The size is less, aperture is less, thin lenses. So define optical center. So 2 points you are right. Optical center means you can see that it is the center point of a lens which lies on the principal axis. And in addition to that, you can say that, and if a ray of light passing through the optical center goes without any bending, so it goes straight. So along third diagram, definition of optical center should be completed. That means along with the third diagram also you can give. Define optical center and draw this third diagram. Third diagram means ray of light passing through optical center goes without any bending, and draw for convex lens and concave lens. So define focal length of a lens. Focal length. Focal length means it is the distance between optical center and principal focus of a lens. Is it clear? So these 3 rays we consider for image formation. What are the 3 rays? First one, ray parallel to principal axis after refraction passes through focus in the case of convex lens, and in the case of concave lens, ray parallel to principal axis after refraction appear to come from the focus. Second one, if a ray is passing through the focus after refraction, it becomes parallel in the case of a convex lens, and ray tends to pass through focus after refraction becomes parallel to the principal axis in the case of concave lens, and ray of light passing through optical center goes without any bending, applicable for both concave and convex lens. I think these points are clear to all of you? Yes. And in the case of mirror, we have seen focal length is related to the radius of curvature by the equation f is equal to r by 2. In the case of lens also, focal length depends upon radius of curvature, but focal length depends not only on radius of curvature, and depends upon the refractive index of the medium in which it is placed. It's a very important one. So when you keep the lens in air or you keep in water, the focal length will change. That is different. It depends upon the medium. So I want to say one point. Focal length of a mirror is independent of medium. Anywhere you keep, focal length remain constant. But focal length of a lens depends on the medium in which it is placed. Okay? Because focal length of a lens depends not only on radii of curvature and depends also on the refractive index. So what that equation we call it as lens maker's formula. Of course, it is not there in class 10, but I can write that equation, give the equation later when I discuss with lens formula. Okay, thank you.